Have you ever gazed up at the night sky, perhaps far away from the city lights, where the stars truly begin to reveal their countless numbers, twinkling like diamonds scattered across an infinite inky canvas? It is a sight that never fails to inspire awe, a profound moment that often leaves us contemplating our place within the grand cosmic tapestry. Yet, in that very moment of wonder, a perplexing question often arises, a paradox that challenges our intuitive understanding of light and vision. Why, amidst the dazzling brilliance of billions upon billions of stars, does the vast expanse of space remain so profoundly dark? It is a cosmic riddle, a fundamental mystery that has puzzled philosophers and scientists for centuries, inviting us to delve deeper into the very nature of light, space, and our perception of the universe itself. On Earth, our experiences with light are profoundly shaped by our atmosphere and surroundings. During the day, the sun, a single star, bathes our world in an overwhelming flood of illumination. Its golden rays penetrate every nook and cranny, scattering off molecules in the air, bouncing off surfaces, and filling our environment with a vibrant, all-encompassing glow. Even at night, artificial lights from cities and towns create a diffuse ambient brightness that prevents absolute darkness in many populated areas. We are accustomed to light filling spaces, to its presence being a tangible, almost physical phenomenon that banishes shadows and reveals the world around us. So, it seems entirely natural to assume that if we were to venture beyond the protective blanket of our planet's atmosphere into the ultimate outside, where countless stars burn with unimaginable ferocity, the heavens would be ablaze with an eternal, uniform brilliance. We might envision space as a dazzling chamber, its walls adorned with an infinite array of cosmic lamps, each contributing its share to a celestial symphony of light. Yet, the reality is startlingly different. As astronauts have repeatedly confirmed, and as our powerful telescopes reveal in breathtaking detail, space, for the most part, is a realm of profound, almost absolute darkness. Even as you look directly at the sun from orbit, an intensely bright orb that could blind you in an instant, the surrounding space remains utterly black. There is no soft, ethereal glow, no diffuse twilight that permeates the void. The stars, despite their immense power, appear as pinpricks of light against an unimaginably deep ebony backdrop, like tiny jewels meticulously placed on velvet. This stark contrast between the blazing intensity of individual celestial bodies and the overwhelming darkness of the space between them is not merely an aesthetic observation. It represents a profound scientific puzzle that forces us to reevaluate our preconceived notions about light and its behavior across the cosmos. Imagine standing on the surface of the moon, or perhaps floating silently in the vacuum far above Earth. The sun, undimmed by any atmosphere, would be a ferocious disk of pure, blinding energy. If you were to shield your eyes from its direct glare, however, you would immediately be plunged into an abyss of darkness. The stars, countless as they are, would still appear as distinct, isolated points of light. There would be no ambient light from the general cosmic background, no gentle illumination from the combined output of billions of distant suns. This observation, simple yet profound, stands in stark opposition to what our earthly intuition might suggest. If the universe is indeed teeming with an unfathomable number of stars, stretching out to distances almost beyond comprehension, then surely their collective light, however faint individually, should accumulate and eventually saturate every corner of the cosmos, making the night sky as bright as day, if not brighter. This is the essence of the cosmic paradox, an apparent contradiction between the vast number of light sources in the universe and the pervasive darkness that defines the space between them. This enigma is not a new one. For centuries, thinkers have grappled with this very question, often framing it in different ways. One of the most famous formulations is known as Olber's paradox, named after the German astronomer Heinrich Wilhelm Olbers, who articulated it clearly in the early 19th century. Although others before him, notably Johannes Kepler and Edmund Halley, had touched upon similar ideas, Olbers' work brought the problem into sharper focus. The paradox, in its simplest form, asks, if the universe is infinite in extent and uniformly filled with stars, then in every direction we look, our line of sight should eventually encounter the surface of a star. If this were true, the entire sky, night and day, would appear as bright as the surface of an average star. Clearly, this is not what we observe. The night sky is dark. This fundamental discrepancy highlights the profound implications of our initial assumption about an infinite, static, and uniformly star-filled universe. The very act of asking, why doesn't the sun light up space, leads us down a fascinating path of discovery, requiring us to examine some of the most fundamental principles of physics and astronomy. It forces us to consider the true nature of light itself, not as a continuous, all-pervading medium, but as discrete packets of energy, photons, that travel at a finite speed. It compels us to understand the properties of the vast emptiness that is space, a near-perfect vacuum, largely devoid of the matter that would allow light to scatter and diffuse. We must also confront the immense scales of the universe, acknowledging the incredible distances that separate celestial objects and the profound impact of these distances on the intensity of light. Furthermore, the paradox compels us to consider the dynamic nature of our universe, its expansion, its finite age, and the limits of what we can actually observe. This initial contemplation of cosmic darkness is not merely an intellectual exercise, it is a gateway to understanding some of the most profound revelations of modern cosmology. The answers to this seemingly simple question are deeply interwoven with our understanding of the Big Bang, the expansion of space, the concept of a finite observable universe, and even the way our own eyes perceive light. By confronting the darkness, we are forced to confront the very structure and evolution of the cosmos itself. It is a journey that will take us from the quantum realm of individual photons to the grandest scales of galactic superclusters, all in an effort to demystify why the boundless brilliance of the universe's stellar furnaces fails to banish the enigmatic shadows of space. This initial paradox serves as our starting point, the compelling question that will guide our exploration into the captivating science behind the universe's most pervasive characteristic, its overwhelming, majestic darkness. The journey into this cosmic riddle promises to illuminate not just the reasons for the night sky's darkness, but also the incredible story of the universe in which we reside. It is a story told in light and shadow, in the propagation of energy across unimaginable distances, and in the very fabric of space-time. To truly grasp why the vastness of space remains cloaked in darkness, despite the ceaseless fiery output of billions of stars, we must first delve into the very essence of light itself. Light, in its most fundamental form, is not a continuous, flowing substance that fills and permeates all available space in the way that water fills a bucket or air fills a room. Instead, light travels as discrete packets of energy, often referred to as quanta, which we specifically call photons. These photons are the fundamental particles of electromagnetic radiation, and they are the universe's tireless messengers carrying energy and information across unimaginable distances. Understanding their nature and how they behave in the cosmic void is absolutely crucial to unraveling our paradox. Imagine a star, any star, even our own sun. Deep within its fiery core, nuclear fusion reactions rage, converting matter into immense quantities of energy. This energy is eventually emitted from the star's surface in the form of these countless photons. Each photon is born with a specific amount of energy, which dictates its wavelength and frequency, what we perceive as its color in the case of visible light. From the moment they escape the star's gravitational embrace, these photons embark on an extraordinary journey, traveling through space at the fastest speed possible in the universe. The speed of light, approximately 299,792,458 meters per second, or about 186,000 miles per second in a vacuum. This speed is a cosmic constant, a universal limit that nothing with mass can ever achieve or surpass. Now, here is the crucial distinction. When a star emits light, it does not somehow fill the surrounding space with a diffuse glow, analogous to a cloud of smoke gradually expanding. Instead, it launches trillions upon trillions of individual photons in every conceivable direction. Think of a colossal cosmic sprinkler, but instead of water droplets, it's spraying individual incredibly fast-moving energy packets. Each photon travels in a straight line from its point of origin, unhindered and uncolliding, until it either strikes an obstacle, like a planet, a dust particle, or your eye, or continues its journey indefinitely, potentially for billions of years across the universe. The path of a photon through the vacuum of space is remarkably straightforward. Unlike light passing through Earth's atmosphere, where it constantly interacts with air molecules, water vapor, and dust particles, causing it to scatter and diffuse, a photon in space encounters virtually nothing. This lack of interaction is paramount. When light scatters, it means that the photons are bouncing off particles, changing direction, and spreading out in a way that allows us to perceive a general illumination. This is why the sky on Earth appears blue during the day. Sunlight is scattered by nitrogen and oxygen molecules, with blue light scattering more effectively. This scattered light fills our atmosphere, making the sky bright and diffuse. Without this scattering, the sky would appear black even during the day, with the sun a blinding disk against it, much like on the moon. In the vacuum of space, however, there are no significant numbers of particles to scatter the light. A photon, once emitted from a star, will travel directly away from that star in a perfectly straight line, like an arrow shot into an infinite void, until it encounters something. If that something is your eye, you will perceive that photon as light coming from that specific star. But the space between your eye and the star, and indeed the space all around the photon's trajectory, remains dark. It is dark because there are no other photons arriving from other directions at that exact point in time to fill that space with light. And critically, there is nothing in that space to scatter the light that is passing through it. Consider a powerful spotlight shining into a perfectly empty, dark room. If there is no dust or smoke in the air, you would only see the beam of light where it hits a surface. The path of the light through the air would be invisible. Introduce some dust or smoke, and suddenly you can see the beam itself, because the light is scattering off the tiny particles. Space is like that perfectly empty room, but on an incomprehensibly grand scale. The spotlights are the stars, and the room is the cosmic vacuum. Since there's no dust or smoke, meaning no significant concentration of matter, for the light to scatter off, the paths of the light beams, the photons, remain largely invisible. We only perceive the light when it directly enters our detectors, whether those are our eyes or sophisticated telescopes. Furthermore, light, while traveling incredibly fast, still takes time to traverse the immense distances of the cosmos. When we look at a distant galaxy, we are not seeing it as it is right now, but as it was billions of years ago. The photons that left that galaxy billions of years ago have been traveling continuously through the vacuum of space, carrying information about their origin. They have not been diffusing or spreading out to illuminate the entire intergalactic medium. They have simply been on a journey. This concept of light travel time is fundamental to astronomy and cosmology, allowing us to peer back into the history of the universe. It also reinforces the idea that light is a directed phenomenon, a stream of particles moving from point A to point B, rather than a pervasive glow that instantly fills every corner of existence. The journey of a photon can be incredibly long and solitary. A photon emitted from the surface of our sun takes approximately 8 minutes and 20 seconds to reach Earth. During this journey, it travels through the vacuum of space, a region almost entirely devoid of matter. There are no air, molecules, no clouds, no dust motes of any significant density to interact with. Consequently, that photon travels in a straight line, unimpeded, until it finally strikes something on Earth, perhaps a leaf, a solar panel, or the retina in your eye. The space it traversed, however, was not illuminated by its presence, nor by the presence of the countless other photons traveling alongside it. Each photon is an individual traveler, minding its own business, not actively working to fill the void with light in the way we might intuitively expect based on our everyday terrestrial experiences. This understanding also helps us appreciate the immense emptiness of space. When we talk about empty space, we are speaking of a region where the average density of matter is extraordinarily low. Even in what we consider interstellar medium, the space between stars within a galaxy, there are only a handful of atoms per cubic centimeter. In intergalactic space, the density drops even further, to perhaps 1 atom per cubic meter or even less. To put this into perspective, the air we breathe has about 25 quintillion, that is 25 followed by 18 zeros, molecules per cubic centimeter. This vast difference in density is the key reason why light behaves so differently in space compared to within an atmosphere. The darkness of space, therefore, is not an active phenomenon, but rather a passive one. It is the absence of actively perceived light. It is not that some force is absorbing the light from the stars. It is simply that the light is not scattering off anything substantial enough to become visible from every angle. Each star acts like a point source of light, radiating photons outwards. If you are positioned directly in the path of some of these photons, you see the star. If you are not, and there is no matter to scatter light from the star towards you, then that particular region of space appears dark. The darkness is essentially the visual representation of the vacuum's emptiness and the directed nature of photon travel. Furthermore, the very concept of lighting up a space implies a diffuse and pervasive illumination. For space to be lit up, the light from various sources would need to be scattered and reflected in such a way that it becomes omnipresent, bouncing around and filling every corner with a glow. This is precisely what happens in our atmosphere during the day. However, without a medium to facilitate this scattering, light continues its journey in straight lines. Imagine a vast, perfectly dark theater. If a single projector shines a beam onto the stage is lit, but the air in the theater remains dark unless there's dust in the air. Space is like that theater, but on a scale so grand it defies easy comprehension and with far less dust than even the cleanest theater. So, when we ask why the sun doesn't light up space, the answer lies in the fundamental behavior of light itself. Photons are tireless, uncolliding travelers. They do not magically diffuse or spread out to fill every inch of the cosmos with illumination. They travel in straight lines until they encounter something carrying their energy directly. The space between the stars and between our eyes and those stars appears dark because there is nothing substantial there to scatter the light in a way that would make it visible to us from all directions. It is a testament to the incredible emptiness of the universe and the precise, particulate nature of light. The darkness is not a void of absence, but a canvas upon which the individual pinpricks of light from distant stars are etched, each telling its own story across the cosmic expanse. This understanding sets the stage for our further exploration into the other factors that contribute to this profound cosmic darkness. Having established that light travels as individual packets of energy, called photons, embarking on straight-line journeys through the cosmos, we now arrive at a critical piece of the puzzle: the nature of space itself. Specifically, we must confront the reality of the cosmic vacuum, an environment so profoundly different from anything we experience on Earth that it fundamentally alters the way light behaves. The absence of a substantial medium to scatter light is perhaps the single most important factor contributing to the pervasive darkness of space. Without something for photons to interact with, to bounce off of, or to be absorbed and re-emitted by, light simply cannot diffuse and spread out to create the ambient illumination we take for granted on our home planet. On Earth, our perception of light is overwhelmingly influenced by the atmosphere. This dense blanket of gases, primarily nitrogen, oxygen, and argon, along with trace amounts of other elements and compounds, acts as a colossal scattering agent. When sunlight enters the atmosphere, it doesn't just pass through untouched. Instead, countless photons collide with, or are deflected by, the myriad of molecules and tiny particles suspended in the air. This process, known as scattering, is what gives our sky its brilliant blue hue during the day. Shorter wavelengths of light, like blue and violet, are scattered more efficiently by the small molecules in the atmosphere than longer wavelengths like red and yellow. This scattered blue light reaches our eyes from all directions, making the sky appear bright and uniformly colored. Without this scattering, the sun would be a blinding disk in a pitch-black sky, even at noon, and stars would be visible all day long. This is precisely what astronauts observe from orbit, or what anyone standing on the moon would see. The situation in space, however, is dramatically different. Space is, for all intents and purposes, a near-perfect vacuum. This is not to say it is absolutely, completely empty. No region of the universe is truly devoid of everything. There are always some particles, stray atoms of hydrogen and helium, electrons, cosmic rays, dust grains, and even dark matter and dark energy, the mysterious components that dominate the universe's mass and energy budget. However, the density of this matter is incredibly, mind-bogglingly low. To give you a sense of scale, in the air at sea level on Earth, there are approximately 25 quintillion, that is, 25 followed by 18 zeros, molecules in every single cubic centimeter. In the space between stars within our galaxy, known as the interstellar medium, the density drops to about 1 to 10 atoms per cubic centimeter. In the vast, largely empty regions between galaxies, the intergalactic medium, the density plummets even further, to perhaps 1 atom per cubic meter or even less. This profound emptiness means that when a photon embarks on its journey from a distant star, the probability of it encountering another particle is incredibly slim. For all practical purposes, it travels unimpeded and uncollided for vast stretches of space and time. Imagine shining a powerful laser beam across a football field. If the air were filled with smoke, you would clearly see the beam's path. But if the air were perfectly clean, you would only see the spot where the laser hits the far wall. The beam itself would be invisible. Space is like that perfectly clean air, stretched across distances that dwarf a football field into utter insignificance. The photons from stars are like those laser beams. They are there, traveling, but without anything to scatter them into our line of sight from intermediate points. The space they traverse remains visually dark. The scattering of light is not just about making the sky blue. It is about diffusion, about light effectively filling a volume. When light scatters, it changes direction, and some of it gets redirected towards our eyes from various points in space. This creates an ambient glow, a general illumination. Without a medium to facilitate this, light from a star simply radiates outwards in diverging straight lines. As you move further away from the star, the photons continue to spread out. If you are not in the direct path of any of these photons that are headed towards your detector, that specific spot in space will appear dark to you. It's not that light isn't present or passing through that region. It's that there's nothing there to redirect it towards your perception, nothing to make it visible from an arbitrary vantage point. Consider the analogy of a dense forest versus an open field. In a dense forest, light struggles to penetrate directly to the ground. Instead, it bounces off leaves, branches, and the trunks of trees, creating a diffuse, dappled light throughout the undergrowth. In an open field, however, the sun shines directly. There's nothing to scatter its light, so shadows are sharp, and the space between you and the sun, while bathed in light, doesn't glow with an internal radiance in the same way the forest canopy might. Space is the ultimate open field, a vacuum so vast and empty that there are no leaves or branches for the light to scatter off. Even when light encounters matter in space, such as a planet, a moon, or a nebula, it behaves predictably. When sunlight strikes the moon, for instance, it is reflected. We see the moon not because it produces its own light, but because it acts as a giant mirror, reflecting a fraction of the sun's photons towards Earth. The space between the sun and the moon, and between the moon and Earth, remains dark. Similarly, nebulae, those magnificent clouds of gas and dust, glow spectacularly. But they do so only when they are close enough to hot, luminous stars whose light excites the atoms within the nebula, causing them to emit their own light, or when the dust within them is dense enough to scatter starlight, creating what are known as reflection nebulae. Even in these seemingly illuminated regions, the glowing is localized to the actual matter present. The vast emptiness surrounding these celestial objects remains dark. The profound emptiness of space also means that there is very little to absorb the light energy and then re-emit it as a general glow. On Earth, objects absorb sunlight and then radiate some of that energy as heat, and sometimes as visible light if they are incandescent. But in the near-perfect vacuum, the few scattered particles are too far apart and too sparse to collectively absorb and re-emit enough light to create any widespread illumination. Each particle that might scatter a photon is an isolated event, not part of a continuous medium. Furthermore, the very concept of brightness is often tied to the intensity of scattered light reaching our eyes from multiple directions. When we say a room is bright, it means light is bouncing off walls, ceilings, and objects, filling the space with a generalized illumination. In space, there are no walls or ceilings to bounce light off of. Each celestial body is an isolated island of light, a point source in an ocean of darkness. The light from a star travels outwards, and its intensity diminishes rapidly with distance. By the time it reaches a point far from its source, the number of photons passing through a given area is so small that it is insufficient to create any diffuse brightness, especially when there's nothing there to scatter the few photons that are passing through. The absence of an atmosphere also means that there is no atmospheric refraction, the bending of light as it passes through different densities of air, which can subtly diffuse and spread light around obstacles on Earth. In space, light rays travel in perfectly straight lines, making shadows incredibly sharp and defined, illustrating the direct, unscattered path of photons. The edge of a shadow cast on the moon is remarkably crisp, a testament to the lack of an atmosphere to blur or diffuse the sun's rays. In essence, the vacuum of space acts as a perfect insulator for light. It allows light to travel efficiently and directly, but it does not facilitate the spreading or diffusion of light in the way a material medium would. If you are not looking directly at a light source or at something reflecting light directly to you, then the region you are observing will appear dark. The darkness of space is not an active force absorbing light. It is a passive consequence of the extreme emptiness and the direct, unhindered journey of photons. It is a canvas of nothingness upon which the occasional glorious brushstrokes of starlight are painted, sharp and distinct, emphasizing the profound void between them. This cosmic vacuum, far from being truly empty, is a testament to the fact that even the most fundamental force of light requires a medium to perform its terrestrial magic of pervasive illumination. Without that medium, light remains focused and directional, leaving the vast majority of the cosmos in its majestic, profound, and utterly logical darkness. As we continue our journey into the enigma of cosmic darkness, having understood the particulate nature of light and the profound emptiness of space, we must now turn our attention to one of the most fundamental laws governing the behavior of light, the inverse square law. This principle, while elegantly simple, plays an absolutely critical role in explaining why the light from even the most powerful stars rapidly fades into imperceptibility across the vast cosmic distances, contributing significantly to the overall darkness of the universe. It is a law that dictates how light, and indeed many other forms of energy and force, diminishes in intensity as it travels away from its source, and its implications for our perception of space are profound. Imagine a single, powerful light bulb in the center of a perfectly dark, infinitely large room. When you stand very close to that light bulb, its brilliance is overwhelming, perhaps even painful to your eyes. The light appears intensely concentrated. Now, imagine stepping back, one pace at a time, away from the bulb. With each step, the light appears less bright, less intense. The overall illumination it provides diminishes, becoming weaker and more diffuse as you increase your distance. This is not because the light bulb itself is producing less light, nor is it because some mysterious force is absorbing the light. It is a consequence of the light spreading out over an ever-increasing area as it radiates outwards from its source. The inverse square law quantifies this observation with mathematical precision. It states that the intensity of a physical quantity, such as light, sound, gravity, or an electric field, is inversely proportional to the square of the distance from the source. In simpler terms, if you double your distance from a light source, the light intensity you perceive does not just halve, it becomes 1/4 of its original strength. If you triple your distance, the intensity drops to 1/9, and if you increase your distance by a factor of 10, the intensity plummets to 1/100th. The effect is dramatic and rapid. Let us visualize this with our cosmic sprinkler analogy. When a star emits photons, it launches them in all directions, radiating outwards in a spherical pattern. Imagine a sphere drawn around the star. All the photons emitted by the star must pass through the surface of that sphere. Now, imagine a larger sphere, twice the radius of the first one, also centered on the star. The surface area of a sphere is given by the formula 4 times p times the radius squared. If you double the radius of the sphere, its surface area increases by a factor of 4. Therefore, the same number of photons, spread over an area 4 times larger, means that the density of photons, the number of photons passing through a given unit of area, becomes 4 times less. This is why the light intensity decreases with the square of the distance. The total amount of light remains the same, but it is spread thinner and thinner across an ever-expanding wave front. This physical reality has enormous consequences for our view of the universe. Stars, even the most colossal and luminous ones, are incredibly far away. Our own Sun, a relatively average star, is approximately 150 million kilometers, or 93 million miles, from Earth. The next nearest star, Proxima Centauri, is about 4 light-years away, a distance equivalent to approximately 40 trillion kilometers, or 25 trillion miles. This means that the light from Proxima Centauri has spread out over a sphere with a radius of 40 trillion kilometers by the time it reaches us. The intensity of its light, by the time it arrives at Earth, is minuscule compared to its brilliance at the source, and certainly compared to the Sun's light. Consider the immense energy output of a star. Even if it is producing quadrillions of watts of power in the form of light, that energy is not focused in a single direction. It radiates outwards uniformly into 3-dimensional space. As the distance from the star increases, the light cones from individual photons diverge, and the photons themselves become vastly separated in the immense volume of space. By the time light from a truly distant star, perhaps thousands or millions of light years away, finally reaches our eyes, the original concentrated stream of photons has become so incredibly dispersed that only a tiny, almost negligible fraction of its original output actually intercepts our planet, let alone the tiny pupils of our eyes. The dimness of distant stars is not an optical illusion or a trick of perception. It is a direct, measurable consequence of the inverse square law. Even with powerful telescopes that can collect light from faint sources across vast distances, the light they capture is extraordinarily weak. These telescopes work by having large mirrors or lenses that can gather a greater number of those widely dispersed photons, effectively acting as enormous light buckets. But even with these instruments, the individual photons arriving from distant galaxies are few and far between, requiring long exposure times to accumulate enough light to form a discernible image. This phenomenon explains why, despite the sheer number of stars in a galaxy, or the number of galaxies in the universe, their combined light does not create a uniformly bright background. Each star, each galaxy, is a point source of light, and its contribution to the overall illumination of any particular point in space diminishes incredibly rapidly with distance. By the time light from a galaxy billions of light years away reaches us, its individual photons are so scattered and sparse that their collective contribution to the ambient light is almost infinitesimal. They appear as faint smudges or pinpricks of light, not as a general glow. To further illustrate, imagine holding a flashlight. Close up, it produces a concentrated beam. If you shine that flashlight at a wall a few feet away, you see a bright circle. Now, if you could shine that same flashlight at a wall a mile away, the light reaching that wall would be incredibly weak and spread out over a much larger area, making it barely perceptible, if at all, without specialized equipment. The flashlight itself hasn't changed, but the effect of its light has been diluted by distance. Stars are like unbelievably powerful flashlights, but the walls we are observing, our eyes or telescopes, are often millions or billions of miles or even light years away. This rapid dilution of light intensity with distance is a fundamental reason why space appears dark. While there are indeed countless stars, their light simply does not have the collective power to fill the vast voids between them with a perceptible glow. Each star's light contributes only to a very limited local region around itself. Beyond a certain distance, its individual contribution to the ambient light becomes so infinitesimally small that it effectively becomes undetectable, especially when contrasted with the direct bright light from closer objects. Consider the situation within a dense cluster of stars, like a globular cluster, where hundreds of thousands or even millions of stars are packed into a relatively small volume. Even there, while the night sky would be far more spectacular and brighter than ours, with stars appearing much closer and more numerous, the space between those stars would still appear dark. The inverse square law would still be in effect, ensuring that the light from any individual star diminishes rapidly, and only the light from the very closest stars would contribute significantly to the perceived brightness at any given point. The vast majority of the volume within the cluster would remain dominated by the emptiness and the rapid fall-off of light intensity from any particular source. Moreover, our eyes, and indeed most optical instruments, have a threshold of sensitivity. Below a certain intensity, light simply isn't detected. The photons might still be present, traveling through space, but if their density is too low or their energy too weak, our visual system cannot register them. The inverse square law ensures that for the vast majority of the universe's volume, the light intensity from distant sources falls well below this threshold. This means that while light is constantly passing through every region of space, it is often too faint, too diffuse, and too sparsely distributed to be perceived as an ambient illumination. The inverse square law is not unique to visible light. It applies to all forms of electromagnetic radiation, from radio waves to gamma rays. It also governs gravitational forces, which is why the gravitational pull of a distant star is negligible compared to the pull of our own Sun or Earth. This fundamental scaling relationship ensures that long-range forces and emissions rapidly diminish in strength, localizing their effects. In the context of light, it means that while stars are powerful beacons, their light is very much a local phenomenon in terms of its ability to brightly illuminate its surroundings. The darkness of space, then, is not merely a question of how much light is out there, but also how that light is distributed and how its intensity diminishes over immense distances. The inverse square law is a cruel mistress for light, relentlessly diluting its power across the cosmic stage. It means that while the universe is indeed brimming with light sources, the overwhelming majority of that light is simply too spread out, too faint, and too distant to collectively illuminate the vast voids. Each photon carries its energy directly, and as these paths diverge, the density of energy per unit area decreases dramatically. This principle, in conjunction with the vacuum of space, ensures that the overwhelming visual characteristic of the cosmos remains its profound and enigmatic darkness, punctuated only by the discrete, distant brilliance of stars and galaxies. Our journey into the profound darkness of space has so far illuminated the individual nature of light as photons and the critical role of the cosmic vacuum, along with the inverse square law's relentless diminishing of light intensity over distance. However, for centuries, a deeper, more philosophical question lingered, challenging these initial understandings and pushing astronomers to confront the very structure of the universe itself. This question is encapsulated in what is famously known as Olber's conundrum, or Olber's paradox. It is a thought experiment that on the surface seems deceptively simple, yet it probes the deepest aspects of cosmology and compels us to rethink our assumptions about the universe. The paradox, in its most classic formulation, asks, if the universe is infinite in extent, uniformly filled with stars, and has existed for an infinite amount of time, then why is the night sky dark? If we were to look in any direction, our line of sight, given an infinite number of stars, should eventually land on the surface of a star. Every single patch of the sky, no matter how small, would appear as bright as the surface of an average star, just like looking into a dense, infinite forest, where every direction eventually leads to a tree trunk. If this were true, the entire night sky, far from being dark, would be blindingly brilliant, as bright as the surface of our own sun, if not brighter. Clearly, this is not what we observe. The night sky is undeniably dark, a cosmic canvas punctuated by discrete points of light, not an overwhelming, uniform glow. This glaring discrepancy between a seemingly logical expectation and the observed reality is the essence of Olber's conundrum. While the paradox is named after the German astronomer Heinrich Wilhelm Olbers, who articulated it clearly in 1823, the idea had been contemplated by other great minds long before him. Johannes Kepler, in the early 17th century, grappled with a similar notion when considering the implications of an infinite universe. Later, in the 18th century, the Swiss astronomer Jean-Philippe de Chezot and the English astronomer Edmund Halley also explored aspects of this problem. Olbers, however, presented it in a way that truly captured the scientific imagination and forced a re-evaluation of cosmological models. Let us unpack the core assumptions of the paradox. First, it assumes an infinite universe. This means that if you traveled in a straight line in any direction, you would never reach an edge. The universe would simply go on forever. Second, it assumes a uniform distribution of stars throughout this infinite space. This implies that no matter where you are, the average density of stars in any large volume of space is roughly the same. Third, and critically, it assumes an infinitely old universe, one that has existed forever, allowing light from even the most distant stars sufficient time to reach us. Under these assumptions, the cumulative light from an infinite number of stars, even accounting for the diminishing brightness of individual stars due to the inverse square law, should theoretically sum up to an infinitely bright background. The intuitive counter-argument often raised is that distant stars are simply too far away to contribute significantly to the total brightness, their light having diminished too much due to the inverse square law. However, Olbers' paradox deftly addresses this. While the light from an individual distant star is indeed fainter, there are proportionally more distant stars. Imagine concentric shells of stars around our observation point. A shell that is twice as far away will have 4 times the volume and therefore 4 times as many stars, assuming a uniform distribution. While each star in that shell is 4 times fainter due to the inverse square law, the 4 times greater number of stars means that the total amount of light received from that shell would be roughly the same as from the closer shell. If there are infinitely many such shells, and each contributes a finite amount of light, then the sum of all this light would indeed be infinite, or at least saturate the sky. So, why then is the night sky dark? The darkness of the night sky serves as powerful observational evidence that at least one of Olbers' fundamental assumptions must be incorrect. It tells us something profound about the true nature of our universe, something that was not fully understood in Olbers' time. The solutions to the paradox are not singular, but multifaceted, each touching upon revolutionary insights in modern cosmology. One initial thought might be that interstellar dust and gas absorb the light from distant stars, thus dimming the background. While interstellar dust certainly exists and does absorb some starlight, particularly within galaxies, this explanation is ultimately insufficient. If the universe were infinitely old and filled with light, this dust would eventually absorb so much energy that it would heat up to the temperature of the stars themselves and begin to glow, re-emitting the light it absorbed. This would once again lead to a bright night sky. So, absorption by dust alone cannot solve the paradox. The true solutions to Olbers' paradox lie in addressing the flawed assumptions about the universe's age and its dynamic nature. The first major revelation came with the understanding that the universe is not infinitely old. Instead, it had a beginning, the Big Bang, approximately 13.8 billion years ago. This means that light from stars beyond a certain distance simply has not had enough time to reach us. There is a cosmic horizon, a limit to the observable universe, defined by how far light could have traveled since the Big Bang. We can only see objects whose light has had sufficient time to reach Earth within the age of the universe. This finite age means that there isn't an infinite number of stars whose light has already arrived at our location to cumulatively brighten the sky. Many distant stars and galaxies, while they exist, are simply too far away for their light to have reached us yet. Their photons are still on their journey, traveling through space, but they haven't arrived at our cosmic doorstep. This concept of a finite observable universe directly counters the assumption of an infinitely old universe. Because the universe has a finite age, the number of stars whose light we can possibly observe is also finite. Therefore, the sum of their light, even if it were not spread out, would be finite, and not necessarily enough to overwhelm the darkness. The visible portion of the cosmos, though vast, is not infinite. We are gazing into a cosmic sphere of influence, and beyond its boundary, the light hasn't caught up with us. The second critical solution to Olber's paradox arises from the discovery of the expanding universe. In the early 20th century, observations by Edwin Hubble and others confirmed that the universe is not static, but is actually expanding. Galaxies are, on average, moving away from one another, and the farther away they are, the faster they recede. This expansion has a profound effect on the light traveling through space, a phenomenon known as cosmological redshift. As light waves travel through expanding space, their wavelengths are stretched. This stretching shifts the light towards the red end of the electromagnetic spectrum, and crucially, it reduces the energy of the photons. When light is redshifted, it effectively becomes dimmer and less energetic. The visible light from very distant galaxies can be redshifted so severely that it shifts out of the visible spectrum entirely, becoming infrared, microwave, or even radio waves. While these forms of radiation are still present, our eyes cannot detect them. Furthermore, the stretching of wavelengths also means that the rate at which photons arrive at our detectors is reduced. It's as if the pulses of light are arriving less frequently, further diminishing the perceived brightness. This cosmological redshift therefore acts as an additional mechanism beyond the inverse square law to dim the light from distant sources, pushing many of them below our detection threshold and out of the visible spectrum. So, while there might be an infinite number of stars in a truly infinite universe, the combination of a finite observable universe, due to its finite age, and the dimming effects of cosmological redshift, due to its expansion, provides compelling explanations for the dark night sky. The darkness is not a sign of an empty universe, but rather a profound indicator of its dynamic nature, its finite past, and its continuous evolution. It's a cosmic window into the Big Bang itself. Olber's paradox, initially a perplexing conundrum, thus becomes a powerful tool that guided astronomers towards a more accurate understanding of the cosmos. The dark night sky, far from being, and by absence of information, is a rich source of clues about the universe's age, its expansion, and its overall structure. It tells us that we live in a universe with a distinct history, a beginning, and a dynamic future rather than a static, infinitely old and uniform expanse. The darkness of space is not a failure of starlight, but rather a testament to the universe's grand narrative and its fundamental physical laws at play across unimaginable scales. It transforms a simple observation into a cornerstone of modern cosmology, showcasing how an apparent paradox can unlock profound truths about our existence. Our exploration into the reasons behind the pervasive darkness of space has brought us to a profound realization. The universe is not static. It is a dynamic, evolving entity, and its most dramatic characteristic, its expansion, plays an absolutely pivotal role in explaining why the collective brilliance of billions of galaxies fails to illuminate the cosmic void. This cosmic expansion gives rise to a phenomenon known as cosmological redshift, an effect that not only stretches the very fabric of space, but also stretches the light waves traveling through it, effectively dimming and changing the color of light from distant sources. This stretching, this redshift, is a crucial component in unraveling the mystery of the dark night sky, working in tandem with the finite age of the universe and the inverse square law. To understand cosmological redshift, we must first grasp the concept of an expanding universe. For much of human history, it was assumed that the universe was eternal and unchanging on large scales. However, groundbreaking observations in the early 20th century, most notably by Edwin Hubble, revolutionized this view. Hubble, observing distant galaxies, noticed a systematic pattern. Almost all galaxies were moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This was not because we are at a special center of the universe, but because the very fabric of space-time itself is expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon. The galaxies themselves are not moving through space. Rather, the space between them is expanding. This expansion has a direct and measurable effect on light. Light travels through space as electromagnetic waves. Imagine these waves as ripples on the surface of an expanding balloon. As the balloon inflates, the distance between the ripples themselves increases, effectively stretching their wavelength. Similarly, as light journeys across the vast, expanding stretches of the cosmos, the space through which it travels continuously stretches. This stretching of space-time causes the wavelength of the light to also stretch. When the wavelength of light stretches, it shifts towards the red end of the electromagnetic spectrum, a phenomenon known as redshift. It is important to distinguish cosmological redshift from the more familiar Doppler effect. The Doppler effect occurs when a source of waves is moving relative to an observer. If a star is moving away from us, its light waves get stretched, resulting in a redshift. If it is moving towards us, the waves get compressed, resulting in a blue shift. Cosmological redshift, however, is not primarily due to galaxies moving through space, but rather due to the expansion of space between the source and the observer. While galaxies do have their own peculiar velocities, their motion relative to the local cosmic expansion, the dominant effect for very distant galaxies is the cosmological redshift caused by the expansion of space itself. This stretching of light waves has two critical consequences for why space appears dark. First, as light's wavelength increases, becomes more red, its energy decreases. According to Planck's equation, the energy of a photon is inversely proportional to its wavelength. So, a photon that has been significantly redshifted has lost energy. This means that the light arriving from extremely distant galaxies is not only spread out by the inverse square law, but each individual photon carries less energy than it did when it was originally emitted. This makes the light intrinsically fainter and less potent. Imagine trying to illuminate a vast hall with dimming flashlights. The effect of each light source becomes drastically reduced. Second, and perhaps even more profoundly, Cosmological redshift can shift light out of the visible spectrum entirely. Our eyes are sensitive only to a very narrow band of electromagnetic radiation from red to violet. Light emitted by distant stars and galaxies, which might have been visible light when it was first produced billions of years ago, can be stretched by the expansion of the universe until its wavelength becomes so long that it falls into the infrared, microwave, or even radio wave portions of the spectrum. For example, light that was originally blue or green from a galaxy billions of light years away might arrive at Earth as faint infrared radiation. While instruments like infrared telescopes can detect this light, our eyes cannot. This means that a substantial portion of the light that has reached Earth from the most distant parts of the observable universe is simply invisible to us. Consider a galaxy so far away that its light has been traveling for, say, 10 billion years. During that immense travel time, the space between that galaxy and us has expanded enormously. A photon that began its journey as a vibrant blue light wave with a relatively short wavelength would have its wavelength stretched continuously as it traversed the expanding cosmos. By the time it finally arrives at Earth, that blue light might have been stretched to a wavelength that corresponds to infrared radiation or even microwaves. So, even though the photons are present, they no longer stimulate the photoreceptor cells in our eyes that detect visible light. This is an incredible effect of the universe's dynamic nature, transforming what was once brilliant starlight into an undetectable cosmic whisper, at least to our natural senses. Furthermore, the expansion of the universe also affects the rate at which photons arrive from distant sources. As space expands, it not only stretches individual light waves, but also increases the average time interval between the arrival of successive photons. Imagine two photons being emitted from a distant star, one right after the other. As they travel through expanding space, the distance between these two photons increases. This means that if you are observing from Earth, you will detect them arriving at a slower rate than they were emitted. This phenomenon is called time dilation, and it further contributes to the perceived dimness of distant objects. Fewer photons arriving per second translates directly into a lower observed intensity of light. This is yet another mechanism, beyond the inverse square law and the energy loss of individual photons, that reduces the overall brightness we observe from the most remote parts of the cosmos. Therefore, the combined effects of cosmological redshift, the reduction in photon energy, and the shift of visible light into invisible wavelengths, coupled with the reduced arrival rate of photons, significantly diminish the contribution of distant celestial objects to the overall illumination of space. It's not just that the light is spread out, it's also that the light itself is fundamentally altered and made less effective at illuminating our visible environment. The farther we look, the more pronounced these effects become, until the light from the most distant galaxies is rendered either too faint to detect or completely shifted out of our visual range. This provides a crucial part of the answer to Olbers's conundrum. Even if the universe were truly infinite and contained an infinite number of stars, the expansion of space would ensure that the vast majority of light from very distant sources would be so red-shifted and diluted that it would contribute negligibly to the visible brightness of the night sky. The collective light that might theoretically saturate an infinitely old, static universe is effectively diminished and hidden from our perception by the universe's dynamic expansion. The universe, in its grand design, actively works against the creation of a uniformly bright cosmic background. The expansion acts as a cosmic dimmer switch, gradually turning down the visible light from everything far away, transforming brilliant stellar emissions into a faint, invisible glow. This is why, when we observe the most distant regions of the universe with powerful telescopes, we are not looking into a bright, uniformly illuminated past, but rather a past where light, though once brilliant, has been profoundly affected by billions of years of cosmic expansion. The profound darkness of space, then, is a direct consequence of the universe's own growth. It is a visual testament to the Big Bang and the continuous stretching of space-time that began nearly 14 billion years ago. Without this expansion and the resulting cosmological redshift, the assumptions of Olber's paradox might hold, and our night sky might indeed be an unbearably bright, featureless expanse. But because our universe is not static, because it is alive with motion and expansion, the light from distant realms is weakened and made invisible to our eyes, ensuring that the overwhelming characteristic of space remains its magnificent, humbling darkness. It is a darkness filled with the ghosts of ancient light, still traveling, still carrying information, but transformed beyond our immediate visual recognition. Having delved into the individual nature of light, the profound emptiness of the cosmic vacuum, the relentless diminishing of light intensity by the inverse square law, and the transformative effect of cosmological redshift due to the universe's expansion, we arrive at another cornerstone in understanding the dark enigma of space, the concept of a finite observable universe. This concept is intrinsically linked to the age of the cosmos and the ultimate speed limit of light, together creating a cosmic horizon beyond which light simply has not had enough time to reach us. It's not just that light is dimmed or stretched. It's that vast swaths of the universe are, quite literally, beyond our visual reach, their light still traveling, still journeying through the cosmic expanse, but yet to arrive at our vantage point. Imagine standing in a vast, ancient forest at dawn. The sun has just risen, and its first rays are piercing through the trees, illuminating the immediate surroundings. However, if you look far off into the distance, especially in denser parts of the forest, it might still appear dark. That's not because those distant trees aren't being lit by the sun. It's because the light hasn't traveled far enough yet to reach them, or to reflect back to your eyes from them. The light is on its way, but it hasn't completed its journey. The universe operates on a similar, albeit vastly grander, principle. The universe, as we understand it through the Big Bang theory, is not infinitely old. It had a beginning, a moment of immense density and heat from which it has been expanding and evolving. Current scientific estimates place this beginning approximately 13.8 billion years ago. This finite age is absolutely crucial. Since light travels at a finite, albeit incredibly fast, speed, the cosmic speed limit of 299,792,458 meters per second, there is a maximum distance that light could have traveled to reach us since the Big Bang. This maximum distance defines what astronomers call the observable universe. It is a spherical region of space surrounding us, not because we are at the center of the universe, but because it represents the sphere of our possible perception. Every point in the universe has its own observable universe centered on itself. For us, here on Earth, our observable universe extends approximately 46.5 billion light years in every direction. You might wonder, Why, this number is larger than 13.8 billion light years, the age of the universe. This discrepancy arises because, during the time light has been traveling towards us, the space itself has been expanding. So, an object that emitted light 13.8 billion years ago, and whose light is just reaching us now, is currently much farther away than 13.8 billion light years due to the expansion of the universe. The key takeaway is this: any star, any galaxy, any cosmic structure that lies beyond this observable horizon is, by definition, unseen by us. Its light has simply not had enough time to bridge the immense cosmic distances and reach Earth. It's like waiting for a message that was sent billions of years ago from a place billions of light years away. If the universe is 13.8 billion years old, then any message from an object that is 20 billion light years distant from its point of emission, whose light has taken 20 billion years to reach us, simply hasn't arrived yet. The photons are still out there, traveling through the vast cosmic expanse, but their journey is incomplete from our perspective. This limitation means that the number of stars and galaxies whose light can possibly reach us is finite. It is not an infinite number, as assumed in the classical formulation of Olber's paradox. Even if the universe beyond our observable horizon contains an infinite number of stars, their light contributes nothing to our night sky's brightness because it has not yet arrived. This directly addresses one of the core assumptions of Olber's paradox, demonstrating that the infinite, uniformly filled, and infinitely old universe envisioned in the paradox simply does not align with our current understanding of cosmology. Think of it as peering into a cosmic time capsule. When you look at a distant galaxy, you are not seeing it as it is today, but as it was billions of years ago, at the moment the light left its surface. The farther away the galaxy, the further back in time you are looking. When we look at objects at the very edge of the observable universe, we are essentially looking back to a time when the universe was very young, just a few 100 million years after the Big Bang. At these extremely early epochs, stars and galaxies were just beginning to form, and they were much less numerous and less evolved than they are today. The universe was simply not yet filled with a dense, uniform distribution of mature, bright stars that could collectively illuminate the entire cosmos. Furthermore, the very early universe was a very different place. Before stars and galaxies began to fully form, the universe was largely a hot, dense plasma, and then later a dark soup of neutral hydrogen and helium atoms after recombination. This period, known as the Dark Ages, lasted for hundreds of millions of years before the first stars ignited. So, even if we could peer beyond our current observable horizon, we would eventually reach a point in time before most stars even existed. This further underscores why a uniformly bright sky is impossible. The light-emitting sources themselves were either not yet formed or were too sparse in the early stages of the cosmos. The concept of a finite observable universe also highlights the vastness of the unobservable universe. While we can only ever see a limited portion of the cosmos, theoretical models suggest that the actual universe extends far, far beyond our current horizon. There could be countless galaxies and billions upon billions of stars beyond our visual reach, but their light, for all intents and purposes relevant to our night sky, is non-existent to us. This means that a significant portion of the universe's total light output simply hasn't had the opportunity to complete its journey to Earth. Leaving those distant regions, effectively dark from our perspective. This limitation is not about the expansion dimming the light or the vacuum not scattering it, but purely about travel time. It's a fundamental boundary imposed by the speed of light and the age of the universe. If the universe were infinitely old, then eventually light from even the most distant stars would reach us, but it is not. The clock started ticking 13.8 billion years ago, and that sets a definitive limit on what we can possibly see. Consider the ramifications. We are surrounded by a sphere of observability. Within this sphere, light from cosmic objects has had enough time to reach us. Outside this sphere, the light is still en route. This means that for any given point in space, there's always a future light arriving from regions that are currently unobservable to us. As time passes and the universe ages, the observable universe slowly grows larger, allowing light from increasingly distant objects to reach us. So, the night sky is not permanently dark in the sense that no more light will ever arrive. Rather, it's dark because much of the light from the most distant sources simply hasn't arrived yet. This finite light travel time explains why the total amount of light we receive from the cosmos is not overwhelming. The cumulative effect of all light sources, even those that have been red-shifted and diluted, is limited by the number of sources whose light has actually had time to reach us. If there were an infinite number of stars whose light had already reached us, the sky would be bright. But there isn't. The cosmic clock and the speed of light enforce a natural boundary on the light we can perceive. Moreover, the universe is not just finitely old, but also structured. Stars are not uniformly distributed throughout all of space. They cluster into galaxies, and galaxies cluster into groups and superclusters, with vast, relatively empty voids in between. This clustering means that while galaxies are numerous, there are immense volumes of space where the density of light-emitting objects is exceedingly low. These voids contribute significantly to the overall darkness. Even within galaxies, the space between stars is immense, as we discussed with the inverse square law. The notion of a uniformly filled universe, a key assumption of Olber's paradox, is a simplification that does not reflect the universe's actual large-scale structure. In summary, the dark night sky is a powerful indicator of the finite age of our universe and the existence of an observable horizon. We are effectively looking out into an expanding, evolving cosmos with a definite beginning. The light from objects beyond this horizon is still traveling towards us, and the light from the very earliest epochs of the universe is sparse, or often redshifted out of our visible range. This combination of factors ensures that the total light arriving at Earth from all cosmic sources is finite and insufficient to uniformly illuminate the night sky. The darkness, therefore, is not a void of light, but a testament to the universe's grand narrative, its limited age, and the incredible distances that light must traverse. It is a visual representation of the cosmic time delay, a silent reminder that much of the universe's brilliance is yet to reach our eyes, if it ever will, in a form we can perceive. This finite nature of our observable cosmos is a critical piece of the puzzle, revealing why, despite the boundless energy of countless stars, the space between them remains in profound, majestic darkness. Our intricate journey through the cosmos, exploring the nature of light, the vacuum of space, the diminishing power of distant light, the vastness of an expanding universe, and the limits of our observable horizon, culminates in a consideration of the final, crucial piece of the puzzle: our own perception. Ultimately, how we interpret and experience darkness is deeply intertwined with the remarkable yet limited capabilities of the human eye and the sophisticated processing power of the brain. The profound blackness of space is not merely an objective state of affairs, it is also a subjective experience shaped by our biological instruments and their interaction with the cosmic environment. Our eyes are extraordinary biological cameras, capable of detecting an astonishing range of light intensities, from the blinding brilliance of the midday sun to the faintest glimmer of starlight. They achieve this through a complex interplay of different types of light-sensitive cells: cones, which are responsible for color vision and detail in bright light, and rods, which are far more sensitive to light and enable us to see in dim conditions, albeit without color. However, even these marvels of evolution have their limits. There is a threshold of light intensity below which our eyes simply cannot register the presence of photons. If too few photons strike our retina within a given time frame, our brain perceives nothing, and that nothingness is interpreted as darkness. This physiological limitation is a major reason why much of space appears dark. As we discussed earlier, the inverse square law ensures that the light from distant stars and galaxies is incredibly spread out and faint by the time it reaches Earth. Cosmological redshift further diminishes the energy of these photons and can even shift their wavelengths out of the visible spectrum altogether. Therefore, for vast expanses of space, the number of photons arriving per unit of time and the energy carried by those photons falls below the detection threshold of our eyes. Even though photons might technically be passing through a region, if their density and energy are too low, our eyes will not register them, and that region will appear black. It's not that there is absolutely no light, but rather that there is insufficient light for our visual system to perceive it. Consider the experience of entering a perfectly dark room. Initially, you might see nothing, but as your eyes adapt, your pupils dilate to let in more light, and your rods become more active, you might gradually begin to discern faint outlines or shapes. Your eyes are constantly working to gather whatever photons are available. In the deepest reaches of space, however, there is almost no ambient light to gather. The darkness is so profound that even with maximum adaptation, the space between celestial objects remains visually void because there are simply not enough scattered photons to stimulate our rods into perceiving any general glow. There are no walls or ceilings for light to bounce off of and reach our eyes from multiple angles, creating that diffuse ambient light. The stark contrast between the intense brilliance of individual celestial bodies and the surrounding blackness also plays a significant role in our perception. When you look at a star in the night sky, it appears as a sharp, brilliant point against an utterly dark background. This contrast accentuates the darkness, making it feel even more profound. On Earth, even on the darkest night, there is often some faint glow from atmospheric scattering, distant city lights, or even moonlight that prevents true, absolute blackness. Our visual system is accustomed to these subtle gradations of light and shadow. In space, the absence of any such ambient light source creates an almost shocking clarity to the darkness, making the bright stars stand out with an unparalleled intensity. Moreover, our brains are wired to interpret the absence of visual input as darkness. When the photoreceptor cells in our retina are not stimulated by light, they do not send signals to the brain. or they send signals indicating the absence of light. The brain then constructs our perception of a black, empty void. This is not a trick of the mind. It is a truthful representation of the sparse photon environment. If space were filled with a diffuse glow, our brains would interpret that as brightness. But since it is not, our brains accurately portray it as darkness. It is also important to remember that our eyes evolved under very specific conditions on Earth, primarily for discerning objects in an environment dominated by sunlight, filtering through an atmosphere. Our visual system is optimized for terrestrial conditions where light is abundant and scattering is commonplace. The extreme vacuum and immense distances of space are environments for which our eyes were not specifically designed. While they can perform remarkably well in detecting individual light sources, their ability to perceive a general, pervasive illumination across vast, empty regions is limited by the very physical properties of light and space we have explored. Even if we were to consider other forms of electromagnetic radiation, such as radio waves or X-rays, which are abundant in the universe, our eyes are simply not equipped to detect them. The cosmic microwave background radiation, for instance, is a faint glow of microwaves permeating the entire universe, a relic of the Big Bang. It is the most uniform light source in the cosmos, a true background glow. However, it is entirely invisible to our eyes, residing in a part of the electromagnetic spectrum far beyond our visual capabilities. If our eyes were sensitive to microwaves, the night sky would appear uniformly bright, a stunning testament to the universe's origins. But because they are not, this pervasive radiation does not contribute to our visual experience of a dark sky. This further emphasizes that darkness is a perception tied to our specific sensory limitations. The perception of darkness in space also plays a significant role in our understanding of what empty truly means. On Earth, even seemingly empty air is teeming with molecules. In space, the vacuum is so profound that the sheer emptiness is almost incomprehensible. The darkness visually reinforces this emptiness, allowing our minds to grasp the vast, almost infinite distances between celestial objects. It highlights the incredible isolation of stars and galaxies, each a beacon in an ocean of profound void. This cosmic isolation, visually represented by darkness, is a humbling reminder of the sheer scale of the universe and our own tiny place within it. The psychological impact of this profound darkness cannot be overstated. Astronauts often describe the view from space as both breathtaking and humbling. The sun is an incredibly bright disk, and Earth is a vibrant, colorful jewel. But turn away from these illuminated objects, and the universe instantly becomes a black canvas studded with impossibly bright, yet distant, pinpricks of light. This is a darkness far deeper and more absolute than anything experienced on Earth, free from atmospheric haze or light pollution. It is a darkness that inspires both awe and a sense of infinite mystery. In conclusion, the question, "Why doesn't the sun light up space?" leads us to a symphony of scientific answers, each building upon the last. It is because light travels as discrete packets of energy, photons, rather than a continuous, all-filling medium. It is because space is an almost perfect vacuum, devoid of the matter that would scatter light and create ambient illumination. It is because the inverse square law relentlessly diminishes the intensity of light over the immense cosmic distances. It is because the universe is expanding, stretching the light waves from distant sources through cosmological redshift, making them fainter and often invisible to our eyes. And finally, it is because our own eyes, while remarkably sensitive, have finite limits, unable to perceive the extremely sparse and diminished photons that traverse the vast, dark voids of space. The darkness of the night sky, therefore, is not a void of absence but a profound revelation. It tells us that our universe had a beginning, that it is expanding, that it is structured with immense empty spaces, and that light, despite its incredible speed, takes time to travel across truly incomprehensible distances. It is a darkness that speaks volumes about the very fabric of space-time, the nature of light, and the grand, dynamic story of the cosmos. So, the next time you gaze up at the night sky, remember that its profound blackness is not an absence of wonder, but a testament to the incredible, complex, and still unfolding mysteries of our universe. Thank you for joining us on this illuminating journey into the heart of cosmic darkness. If you found this exploration as fascinating as we did, please consider giving this video a thumbs up and subscribing to the channel for more deep dives into the science of sleep and the universe.